In this lecture, we want to create the ALU or arithmetic and logical unit of 8085 microprocessor. Even though the main goal of this is to tell you about a flag register, but I figured instead of just explaining the flag register, I want to create everything from the scratch so that you have a better intuition of what these things are. Even though a lot of these things I have already covered in my other course, but I want to explain everything from scratch about the ALU. So the ALU of the 8085 microprocessor accomplishes these different tasks. As the name suggests, arithmetic and logical instructions. And in the arithmetic unit, it accomplishes addition, subtraction, increment, and decrement. And in the logical level, it does and, or, XOR, not, clear, compare, shift, and rotate. And always the concept of ALU and flag register, they always relate to each other. That's why we want to explain both of them in the same lecture. But before we start to creating our ALU and talking about all of these, how to implement addition and subtraction, all of these things, we need to first have an understanding about logical units. Even though I thought it would be a good requirement for this course to have an understanding about the logical gates, but I want to give another review about them. First of all, as I said, you know that every one of these things are created using transistors, and we created all of these single elements and logical units in my other course creating a CPU using transistor and logic gates. But here I just go over what every one of these logical unit accomplishes, not how they are created using transistors. So first we want to talk about the AND gate. This we call an AND gate, 2 input, 1 output. We could show them using this figure or this one. Both of them are true. The important factor about this unit is that it has this truth table. But truth table, we mean that if the A and B are like this, then the output would be like this. In fact, if we give A and B two zeros, the output would be zeros. 0, 1, out would be 0, 1, 0, out would be 0, and 2 ones, out would be 1. So we say a NAND gate has 2 inputs and 1 output. And the output is only equal to 1 when both inputs are equal to 1. Otherwise, it is equal to 0. The same thing about others. This is called an OR gate. Again, you could just show them using both of these shapes. The out would be equal to 0 only when both inputs are equal to 0. Otherwise, the out is equal to 1. Just look at these through the, I'm sure you already understand what these things are. Then after that, we get to the NAND gate. A NAND gate is the, well, we say the knotted of the AND. What I mean is that if we call this a NOT gate, it has 1 input and 1 output. The output is always the complement of the input. So if we put a NOT gate in front of the AND gate, it would just complement all of the output. For example, this is, you already know that this is the truth table of the AND gate, right? This is the out1 voltage levels. If we just NOT all the values, then the corresponding circuit would be called a NAND gate. So we say the truth table of a NAND gate is like this, that the output is equal to 0 when all the inputs are equal to 1. Otherwise, the output is equal to 1. Sometimes we just show the NAND gate like this. Again, the truth table is that out is equal to 0 only when all inputs are equal to 1. And sometimes we just say, and well, you know that if I just put a NOT gate in front of a NAND gate, then an AND gate would be created, just the same thing. And finally, we want to talk about the XOR gate. 2 inputs, 1 output, and the truth table is like this. When both inputs are equal, the output is equal to 0. Otherwise, the output is equal to 1. And this is important. You see, when the inputs are equal to each other, the output is equal to 0 in both cases. And when they differ, the output would be equal to 1.